Temperature is not the degree of hotness or coldness. What is the actual definition, sir?
Now, what we are trying to tell you is, see, by just temperature is actually a degree of hotness and coldness. But what we are trying to tell you is, just by feeling it with our human hands or just by sensing it, we will not be able to get the correct value of temperature. Okay, it is a definition, but that definition in itself cannot be used to measure temperature. We need probes, we need instruments. Okay, we can say that this is warmer, this is colder. Okay, but
Yes,
in
sir.
case of a steel chair and wooden chair, when we say warmer and colder, the real situation is not so. The both of them are going to be at the same temperature. The only thing is depending upon the object. See, if I am a human body, say I am at 98.4 degrees centigrade, and if the surrounding temperature is only 97, then maybe the chair is at 97. Okay, and when I touch it, okay, then immediately there is a temperature difference of about, say I am at 98.4, the chair is 97. So there is about a temperature difference of 1.4 degrees centigrade. Okay, so a certain amount of heat is removed from my body by the chair. Okay, in to attain thermal equilibrium, and I feel that as a coldness. Okay, and the same thing may happen in the same temperature of 97 is there in the wooden chair also, but because that heat transfer is not taking place, I'm not feeling that coldness. Instead, I feel the chair warmer. Okay, so the temperature is a degree of hotness and coldness, but just by sensing it with my human body, by my five senses, I will not be able to define, or I will not be able to measure temperature. That is what we are trying to tell you. We need instruments to measure temperature, and that's why last class we talked about the thermometric properties. Is that clear
Okay,
what
sir.
I have said? Is that clear?
Yes, sir. Yes, sir.
Okay, so now let's go to the presentation. And most of this we have already done. So this is what we discussed in the previous class. We were talking about temperature. So I think the screen is visible. Okay, so we talked about the different temperature probes. Okay, so this class also I forgot to fetch you some instruments. I thought of taking them, but I have forgotten. Okay, one picture will be there. We will discuss it. Okay, so just by using my five senses, I will not be able to measure temperature. So if you look at this, the thermometric property in the table, you can see that. So in the thermometric property, you have various variables like uh, pressure, electrical resistance, EMF induced, radiation, brightness, in some cases, coefficient of thermal expansion. All these will be the properties. So these are the parameters that will change with reference to temperature. Okay, so we require measuring instruments to measure temperature. So our senses in the body will not be sufficient to measure temperature. Okay, so this is what we have been discussing so far. Then temperature scales. We started with this. So we are all familiar with Celsius scale, Fahrenheit scale, and Kelvin scale. And the last class we said the Kelvin scale, one of the temperature is already absolute zero Kelvin. And we just require one more temperature to establish the slope of the linear scale. So we discussed this also. So we talked about ice point and steam point. So ice point and steam point in normal sense, or in a very generic sense, we can call it as the freezing point and boiling point. So 0 degrees centigrade and 100 degrees centigrade. So ice point is 0 and steam point is 100 in case of your Celsius scale and Fahrenheit scale. Okay. So there is one another temperature scale called ideal gas temperature scale. So we haven't talked about ideal gas equation of state yet. Okay, we will be discussing that in the later part of the first unit. What is this? But we have already mentioned if pressure, volume, and temperature they are related by a function, then we call it as an equation of state. So so if your pressure, volume, temperature obeys PV is equal to RT. So P small v is equal to RT, then that is called an ideal gas equation of state, where P is the pressure, V is the specific volume. Specific volume is nothing but volume divided by mass. So any property divided by mass makes it a specific property. You don't have a specific pressure or temperature. So you have specific volume. Volume divided by mass is specific volume. Later on, we will be talking about enthalpy, internal energy, and all these entropy. All these properties can be divided by mass. Okay, and those properties will become specific properties: specific enthalpy, specific entropy, specific heat. Okay, specific internal energy. So all these properties are divided by mass. So if a property is divided by mass, that makes it a specific property. Okay, so if your pressure, volume, temperature is related by this particular function, P small v is equal to RT, where R is a gas constant, we will discuss that later on. Okay, then that is called an ideal gas equation of state. Okay, and this ideal gas equation of state is pertain to a certain region. People call it as um, low temperatures and high pressure region. Okay, low pressure and low temperature region. I'll just we will be discussing that very precisely when we deal with the ideal gas equation of state. Okay, so Van der Waals equation of state, that comes into picture when your temperature is high and the where the dissociation happens, where the temperature is very high, where your individual molecules will come into picture. Okay, we will discuss that separately. Now let's come back to this. So if your pressure, volume, temperature is related by P small v equal to RT, that is called your ideal gas equation of state. Okay, and the temperature scale, the ideal gas temperature scale, it is identical to the Kelvin scale. Okay, in a Kelvin scale, we have already said one particular point is 0 Kelvin and the other point is any other temperature that we have. Okay, and this is based on the constant volume gas thermometer. So I have shown you a picture and the source I have mentioned. So I have taken this picture from the particular source. So what we have here is, so I'll change the color because sometimes it is not visible to me. Okay, so what we have here is a bulb. Okay, so this is the sensor. So what we have here is the bulb, this is the sensor. So you have a specific amount, that means a measured amount of gas inside this bulb. Okay, and here you have a capillary tube, a tube through which this gas can expand, and that is connected to a U-tube manometer. Okay, so here you have the mercury level, and this entire thing can be taken as a U-tube manometer. A U-tube manometer is used to measure the pressure, and that pressure in turn can be used for measuring temperature. Okay, so based on, say, suppose I am introducing this device into a region where I want to measure temperature. Say I'm putting it in a place where the temperature is, say, 60 degrees centigrade. Okay, I'm putting it in a place where the temperature is 60 degrees centigrade. If I put it there where the temperature is 60 degrees centigrade, what will happen is the gas, which was initially at a room temperature, say 30 degrees centigrade, initially it was at 30. Now, when I put it at 60 degrees centigrade, the gas in this particular region of space, in this bulb, it will start expanding and it will start moving through this capillary tube. Okay, it will start moving through this capillary tube. So, based on the temperature, so if it is 60, it expands to a little bit and it pushes the mercury in the downward direction. So now you will be able to measure the difference in the level of the mercury. So this is one level of mercury and this is the level of mercury in the other limb. The level of mercury in one limb, the level of mercury in the other limb. This gives you the height or the difference in height between the mercury levels. Okay, and maybe you would have done this in physics, or where pressure, the hydrostatic pressure is defined as rho g h, where rho is the density, g is your acceleration due to gravity, and h is the height or the difference in height between the mercury levels. Okay, so your pressure is measured based on this. And this density is nothing but the density of mercury, whichever fluid that you use here. If you are replacing density with water, sorry, I mean mercury with water, then the density value is the density of water. In this particular case, it is the density of mercury. And G value all know. Acceleration due to gravity is always 9.81, and H is the height of the mercury level, which is the difference in the level of mercury between the two limbs. Okay, so and if I put it in another temperature, say lower temperature, I have put it in a region of space where the temperature is 20 degrees centigrade. Then what will happen? Instead of expanding, this gas will contract. This gas will come down. It will not expand. So if the gas is not expanding, I'll change the color here. So if the gas is contracting, then the mercury level will come up. Initially, the mercury was pushed down. Now the mercury level will go up. If the mercury level goes up, the level of mercury in the other limb will come down. Say, suppose it has come down to this state, and here the mercury level has raised up to this state. So now the difference is only this much. So now the new difference in height is, say, let me call it as H1. So the new difference in the level of mercury is H1. So now the new pressure would be rho g H1. Okay, so depending upon the temperature, now I am able to measure the corresponding pressure. And based on this pressure, I don't know this temperature. I just know, for example's sake, I have given it as 20 and 60, but I do not know. So what we will do is, so based on the readings in the scale, the temperature will be computed. Okay, and from this experiment, what we see is the temperature, it varies linearly with pressure. The variation of pressure with respect to temperature is linear. And what is the volume? The volume is constant. Okay, so what we have here is the equation T equal to A plus BP. So the moment I change the color, it becomes invisible. That makes it very difficult. So this, I am using an equation T equal to A plus BP, and this is nothing but an equation which you should have been familiar with in max, which is similar to y equal to mx plus c. So y equal to mx plus c is an equation of a straight line. Okay, so here the graph is between x and y. It is an xy plot. Here the plot is between P and T. Okay, so just like you have an XY plot, so just like you have XY plot, so now you have a pressure temperature plot. So here you have the variation of pressure, and here you have the variation of temperature. Just like your y equal to mx plus c is a straight line like this, your T equal to A plus BP is also a straight line. Okay, so that is another straight line dt equal to A plus BP. Okay, so now what we have here is the ideal gas temperature scale. It is developed, it should be developed, because we know that it is 0 degree centigrade and 100 degree centigrade at ice point and steam point, but that is not an ideal gas temperature scale, that is a Celsius scale. So what we do is we take them as reference. So with that reference values, we are supposed to compute all the other reference values. Okay, so we will be doing a couple of problems in this. So what we will do here is we will assume a value for ice point and steam point. Suppose if I assume the ice point as 0 degree, and if I assume the steam point as 100 degree, okay, then the scale that I develop will be similar to Celsius scale. Instead, if I use my ice point as 32 degree, and if I use the steam point as 212 degree, then the scale that I develop will be similar to the Fahrenheit scale, 32 degree Fahrenheit and 212 degree Fahrenheit, right? And similarly, if I use 273 and 373, it is going to be a Kelvin scale. Okay, so what we will do is we will be using, okay, this is the next scale. So what we will do is we will be solving problems in this. So at that particular point of time, it will be very clear to you. But uh, anyhow, what I'll do is introduce a slide here. So we have said T equal to A plus PB or B into P, similar to mx plus C. Okay, so if I am assuming the ice point is 0 degrees centigrade, okay, so 0 degrees centigrade, I will have A plus B into a corresponding pressure. Okay, so what I have to know is what was the pressure when the temperature was 0 degrees centigrade. So that pressure value will be given by the thermometer. The constant value gas thermometer will tell me what is the value of this PI, or a simple pressure gauge can give me 100 is your steam point. So now you will be able to write another equation which will give you A plus BPS. Okay, say suppose this pressure at the ice point was 1 bar for an example. Okay, so that would make the equation simple as A plus B. Okay, this is just an assumption. I'm not saying it is always 1 bar. For you to understand, I'm taking a value as 1 bar. Say at 100 degrees centigrade the pressure is 1.5 bar. Okay, so what I'll have here is A plus 1.5B. So now you have got two algebraic equation. One algebraic equation is A plus B equal to 0. The second algebraic equation is A plus 1.5B is equal to 100. And you know how to solve this equation. So when you solve this equation, you will get a value for A, you will get a value for B. Is it not? So you will get a value for A and you will get a value for B. Now you know the constant values A and B. And now if a pressure is given, for this particular pressure you will be able to calculate the corresponding temperature. So now if you are able to compute temperatures in this particular sense, now you will be able to create a temperature scale. Okay, because I have used 0 and 100 as ice point and steam point, this temperature scale is similar to a Celsius scale. Okay, so don't worry, we will also be doing some problems in this, and at that time it will be much more clear to you. Okay, the next temperature scale is absolute gas temperature scale. Okay, so in this particular case, the same equation we are taking, T equal to A plus BP. Okay, what I'm doing is, okay, when the pressure becomes 0, that means at absolute 0 pressure, so that is what is mentioned here, absolute pressure of 0. If P is equal to 0, then this product B into P will become 0, which means now the equation is simply T equal to A. Okay, and what they have found out is through experiments, what they have found out is for the absolute 0 pressure, they have found for experiments conducted in the constant volume gas thermometer, irrespective of the amount of gas in the bulb and irrespective of the type of gas in the bulb, it may be oxygen, it may be hydrogen, it may be helium, irrespective of the type of the gas and irrespective of the amount of gas in the bulb, at absolute 0 pressure, they found out the temperature was reaching minus 273.15 degrees centigrade. Okay, so they have conducted it for so many types of gases and with so many amounts of gases, and they plotted these values and they got straight lines, and for three different conditions, A, B, C is for three different conditions, maybe three different types of gases or three different amounts of gases used in the bulb. The only thing is, when the gas was brought to absolute zero pressure, when the pressure was zero, they found that the temperature, these lines, now you have got these lines, right? Three lines I have. So if I extrapolate them onto the temperature scale, if I extend these lines, all these lines are following or falling at one particular point, and that value is minus 273.15 degrees centigrade. And they find that this is the lowest temperature. You can't lower it behind this. So this is the lowest temperature possible that can be obtained by a gas thermometer. And what is this minus 273.15 degrees centigrade? That is equivalent to 0 Kelvin. That is absolute zero pressure and absolute zero temperature. So now I hope it is easy to understand. So now this is your Kelvin scale. So one point is at 0 Kelvin. When I say 0 Kelvin is minus 273.15 degrees centigrade. This thing which is marked or written in the purple color or pink color, that is in degree centigrade. So when you add plus 273, right, to convert degree centigrade into Kelvin, we add 273. The exact value is 273.15. So if you add plus 273.15, it becomes 0 Kelvin. So for the Kelvin scale, one value is already fixed. 0 Kelvin is already fixed. So now you need only one another temperature. So let me change the color now. Say suppose this particular point is already fixed. I know this particular point, 0 Kelvin is fixed. All I need to know is if I find another point here, okay, now I will be able to join these 2 points, and now I have a line. And I can find the slope of the line. What is the slope of the line? Y equal to mx plus c. So similar equal t equal to a plus pb. So which means I will be able to get the value of this b by taking the slope. Okay, and then by at 0 Kelvin I can substitute the value, and I know that the value of a is already minus 273.15. Now I know the value of b, and now I will be able to compute the value of a particular temperature. Okay, so that is your absolute gas temperature scale. Okay, so apart from 0 Kelvin, you have to mention only one more temperature or one corresponding pressure. If you know the corresponding pressure, you will be able to get the temperature. If you know the temperature, you will be able to get the corresponding temperature. Okay, so because I know T equal to A, so that makes it simple. Say suppose if this A becomes 0, if A becomes 0, if I make A 0, then you have the equation T equal to BP. Okay, so T equal to BP, and then you need only, so in this particular case, T equal to BP. So you have T equal to BP. Now you need to know the value of the pressure alone. So if you know the value of the pressure alone, okay, you will be able to simply get the point. Okay, not even, so for absolute gas temperature scale, absolute gas temperature scale, okay, by assigning a value of 0 at the constant A, which means, so there is a slight clarification I have to make here. So initially T equal to A plus BP. Okay. So when the pressure was 0, I simply had T equal to A, which T equal to A. Okay. So here there is a slight confusion. And your A is minus 273.15. Okay, your A is minus 273.15. When did it happen? When your pressure is equal to 0. Okay, so when your pressure is 0, you are getting T equal to minus 273.15. And we said that that is the lowest temperature that can be attained by using a gas thermometer. Okay, one more thing, what they are insisting here is, say suppose you have this T equal to A plus BP. Okay, that is fine. That is your linear line equation. So T equal to A plus BP. Now what I do is I make this A 0. If I make this A 0, then what is left out is T is equal to BP. So here, if the pressure is 0, if the pressure also is 0, then what you will have is T equal to 0 Kelvin, which is minus 273.15. If the pressure value is 1.5 bar or 1 bar, then by knowing the value of B, see here, not even the 0 Kelvin is required. By simply giving the value of a corresponding pressure, you will be just able to get the value of a temperature. So when even my prior statement that for a for a Kelvin scale, you need to measure, you need a temperature apart from 0 Kelvin is itself wrong. What they are telling you is for a Kelvin scale, a simple temperature is sufficient or a simple pressure is sufficient to determine the corresponding temperature. Okay, so that makes Kelvin scale very easy to attain. So that is called the absolute gas temperature scale. Okay, so I have made it a little bit of confusion here. So I need to know whether you guys have understood this. So have you understood this, or should I explain it again?
Yes, sir.
Sir,
Understood.
can you repeat again, sir? I didn't understand the
Okay,
last part, sir.
okay, okay. I'll tell this again. Okay, what is mentioned here in the last two statements is, see, if you look at this, the absolute gas temperature scale can be obtained by assigning a value of 0 to the constant A. We know that this is the fundamental equation, T equal to A plus BB. Now what I do is I assign A equal to 0. So if I assign A equal to 0, what I have is T equal to BP. Okay. Now what is required is I simply need to know what is the pressure value. I already know the value of B. Okay. I would have already computed the value of B. Okay. All I need is the value of this P. Okay. And by knowing it, I will be able to get the value of the temperature. Okay, so what they are telling you is you need to specify the temperature at only one point to define an absolute gas temperature scale. Okay, so this 0 Kelvin is there, but even that 0 Kelvin is not required. All you need to know is you have to simply know a temperature at a point to draw this Kelvin scale. Okay,
Yes, sir. Got it, sir.
okay, clear?
Yes, sir.
Yeah, fine. Let's move on. Um, so this is pressure, and a little bit of explanation is sufficient here because we will not be doing much on this, but this is an important property, a thermodynamic property, which we always come across in the PV diagram. Okay, so you all know the definition of pressure as force per unit area. Okay, but that normal force exerted by the fluid per unit area is pressure. What you should remember is this force per unit area is pressure in case of fluids. Okay, when I say fluids, it is for liquids and gases. So force by area for liquids and gases is pressure. If it is for a solid, then we give it a new name called stress. Okay, stress is also force divided by area, and that stress we normally call it, that force per area we usually call it a stress in case of solids. If it is liquid and fluid, then we call that force per area as a pressure. Okay, and that force is usually a normal force. That means if I have a surface, then the force that acts perpendicular to that surface is called the normal force. Okay, and then you should be aware of this atmospheric pressure, absolute pressure, and gauge pressure. Okay, so when I say atmospheric pressure, the atmospheric pressure you should all be familiar with. Okay, people usually call that as 1 atmosphere. Absolute pressure, sorry, atmospheric pressure, I should have written it above. So your atmospheric pressure is 1 atmosphere, or the usual representation is it is 1.013 bar. Okay. The moment they say the initial state of air is at atmospheric pressure, they won't give you the value. You should always remember it as 1.013 bar. And you should remember this bar is nothing but 1 bar is equal to 10 to the power 5 Newton per meter square. Force per area. That is your pressure, right? And sometimes, not sometimes, this Newton per meter squared can also be represented as Pascal, PA, capital P and small a. Okay, so 10 to the power 5 Pascal is 1 bar. Okay, so that is your atmospheric pressure. So we all know that the atmosphere is exerting certain pressure on the Earth's surface or on the Earth. So we feel that as atmospheric pressure. Okay, but if I am going to measure the pressure of some air which I am holding in a box or in a tube or in some enclosure, okay, and I use some measuring instrument to measure that pressure, okay, and it gives me the reading as 1 bar. Okay, I'm using an instrument and I'm using that instrument to measure the pressure of a liquid in a container, and it is giving me the value as 1 bar. The atmospheric pressure is 1.013 bar, and this pressure is 1 bar. Okay, so whenever you're using a measuring instrument, that measuring instrument will give you the value by taking the atmospheric pressure as the reference. That is the base, which means it takes that as the level from which the measurement is taking place. Okay, so for example, um, uh, I don't have an object here. Um, okay, I have a small toy here. Okay, so this toy, I'm holding it in my hand. Okay, so if I am placing it on my hand like this, okay, I'm simply placing it on my hand like this. Okay, for this particular toy, my hand level is the reference. So I say the height of this particular toy is say 2 centimeters by taking this hand level as the reference. But if you take the height of this toy from the ground, it is not just 2 meters. It is not just 2 centimeters. Okay, it is going to be maybe even 2.5 meters or so. I'm talking about the ground. Even the house that is built is above the ground, maybe a meter high. Okay, not a meter high, 0.5 meters. So approximately 1 meter. So 1 meter and 2 centimeters. So 1.02 meter. So that would be the height of this toy. Okay, now I hope you're able to understand. So similarly, atmospheric pressure is taken as the reference. So that is taken as the base, and your instrument is measuring some pressure. Okay, and that pressure is something like the height of this toy with reference to the surface. So the height of the toy is only 2 centimeter, but that is with reference to the level of my hand. Similarly, your instrument will be giving you the value of the pressure with reference to the atmospheric pressure, and so the value is 1 bar. But what is the actual pressure? It will be 1 bar plus 1.013 bar. So it will be 2.013 bar. So that will be the absolute pressure. That is the total pressure. When I say absolute pressure, that is total pressure. So total pressure is atmospheric pressure plus gauge pressure. So if you look at the diagram, so this is the atmospheric pressure, and this is the absolute zero pressure, where there is no pressure at all, where there is 0 Pascal. The value of pressure is 0. So this is 0 Pascal. Whereas in this particular level, the pressure is 1.013 bar. Okay, these two are references. One is 0 bar, the other one is 0 Pascal or 0 bar. 0 into 0 with anything is going to be 0. So it is 0 bar. The other one is 1.013 bar. Okay. And then you can see that there is another pressure here. One line is drawn here. That is the absolute pressure. And that is nothing but the pressure. So let me use another color because they have already used red. So let me use green. So this is your atmospheric pressure. So this is your atmospheric pressure. And anything that is measured above atmospheric pressure is called the gauge pressure. I use some gauge or measuring instrument to measure it. So that is called the gauge pressure. And if the gauge pressure is positive, it is going to be above the atmospheric pressure. If the gauge pressure is negative, okay, if the pressure of the fluid inside the tube is lower than the atmospheric pressure, then that is going to be negative, right? So that is negative gauge pressure. Okay, so if it is a positive gauge pressure, then total pressure will be atmospheric pressure plus the gauge pressure. If the gauge pressure is negative, then the total pressure will be atmospheric pressure minus the gauge pressure. Is that clear? So you will have only three entities. One is atmospheric pressure, so that is called 1.013 bar. The other one is absolute zero pressure, that there is no pressure at all, literally no pressure, no force is exerted by anything, so that is zero pressure. The third one is the total pressure. Why they are not using the word total is total has got another meaning. So that you will be, I'm not sure, that is not there in the current regulation for you, gas dynamics, that has been lifted up. It has been shifted to elective. So gas dynamics, you'll be talking about a pressure called stagnation pressure. Something is moving, the nose of the airplane which is moving, okay, and the aeroplane is moving in the atmosphere, the surrounding atmosphere, which is still, okay, the air is not, it is not in, it is not in motion, it is still. So as the aeroplane moves, okay, with a particular speed, the air that comes into contact with the nose of the aeroplane or the tip of the aeroplane, okay, that becomes zero. The velocity at that particular position becomes zero. The velocity of the air, because of the velocity induced by the aeroplane, okay, that becomes zero. So when the velocity of the fluid becomes zero, the corresponding pressure is called a stagnation pressure, because the air comes to a standstill. Okay, and that stagnation pressure is something sometimes also called as total pressure. Don't worry about it, we are not studying it. I'm simply trying to tell you that the word total has got another meaning, so people are not using the word total. When we say total, total means a reference plus something, that is total. So here the word total is not used because that word is used somewhere else. So that is why we use a word called absolute pressure. Absolute pressure is atmospheric pressure plus gauge pressure. If the gauge pressure is positive, your absolute pressure will be greater than the atmospheric pressure. If the gauge pressure is negative, your absolute pressure will be lesser than the atmospheric pressure. Hope it is clear to you. Okay. And this one you would have done in your +1 or +2 or even before that, I don't know, barometer, an instrument used to measure pressure. Okay, so here they have got a mercury reservoir. So I'll take the black color. So here you have got a mercury reservoir. So this is the level of mercury in the reservoir, that means in the vessel. Okay, and that is open to the atmosphere. So it is not a closed vessel, it is open to the atmosphere, and you can see an inverted U tube. Okay, and both this vessel and here all this blue colored, blue shaded portion is nothing but your mercury. Okay, say suppose if I take this vessel and put in an environment where the pressure is greater than the atmospheric pressure, what will happen is the pressure will be exerted on the fluid, on the surface. So when excessive pressure is applied on this, so this level will go down, right? So from this level, it may come to this particular level. It may come to this level. So what will happen to the level of mercury in the column? That will go up, right? So that will increase the value, or that will have a change in the value of H. You have an increase in the value of H. So if H increases, your pressure value also increases. I have already told you your H value is proportional to pressure by the relation P equal to rho GH, which is the hydrostatic pressure. Okay, P equal to rho GH. Say suppose the pressure in the surrounding environment is lower, then what will happen? Let me change the color. So then what will happen? The level of the reservoir will rise up, right? And the mercury level will come down. Now you have a new height, and this new height will be lesser than the older height. Okay, and because the height has fallen down, the pressure has also fallen down. Because the height has raised up, the pressure has also raised up. Is that clear? So that is how your barometer measures the pressure of the surrounding air. Okay, so this H varies with the atmospheric pressure, and this barometer and altimeter, they all come together in one setup nowadays. Okay, so now what we will do is, um, in the slides I have a couple of problems. So now I want you to take your notebook, and we will try to solve a couple of problems. So in the last class, what I have done is I have sent you a problem page like this. So there are about 18 problems or 19 problems are there. Actually, pure substance is not included in it, and that will be added separately. And work transfer also, I usually do not take it, but this time around I thought I will introduce that also. So we'll have a couple of problems added to it. And why I take so much problems is, um, I do not know how comfortable with how comfortable you are with problems right now, because the usual trend in the schools is that you people always prefer to write theory questions rather than the problems. Okay, but now that mindset should change. Okay, in a real scenario, solving problems is more easy than writing lengthy, long theoretical questions. And so that mindset should change, and you should be comfortable with problems. Okay, and I've given a lot of problems just to tell you what sort of changes can come in a problem, how to read the problem and how to answer them, and if the problem is lengthy, how easy it is to solve. And you should also have that in mind. I tell this in every class, in thermodynamics or in any thermal subject. If the problem is lengthy, then it is easy to solve. You should understand it first. People panic if they see a lengthy problem. That should not be the case of thermodynamics or any thermal subject, because if you have a lengthy problem, you will have large number of details. Okay, that means you need not go for any assumptions at all. You can have a lot of details, and you can have a variety of formulae to use and come out with a result easily. But if the problem statement is very less, then you should worry, because then you should think about the assumptions, then you should think about which formula to use, which method to apply. And if the problem is lengthy, it is easy. If the problem is very small, only then you have to think about it. Okay, so now please take your notebook and write down this first question. So uh, I leave it to you. Either you can take, if you have a printer at home, you can take this problems page, you can take a printout of it, paste it, and then just simply write the answer. Or you can just copy down the question, leave some space for the question because I have given you the question, and just write down the answers, and later on you can add the question also. Whichever is convenient to you, you can do that. Okay, so now let's proceed. And I think I forgot to mention one thing in the slide, and I'll stress that out while we solve this problem. Okay, so now let's start with the first one. Okay, here the question reads like this: the pressure in a constant gas thermometer. The moment you look at the question like this, the pressure in a constant gas thermometer is in a constant gas thermometer. So this constant gas thermometer is the key. The moment you look at it, then you should immediately recognize that in a constant gas thermometer, temperature varies linearly with pressure. Immediately, the equation T equal to A plus PB should come into your mind. Is that clear? Okay. So constant gas thermometer, immediately you should recognize temperature varies linearly with pressure. Okay. Let's see. The pressure in a constant gas thermometer is measured as 32 millimeter of mercury above the atmospheric pressure at triple point. I'm not sure whether I have mentioned this triple point. This triple point is nothing but the temperature at which ice, water, and steam coexist. So it is at this triple point, you can see, you can have a mixture of ice, water, and steam. All of them can stay together comfortably as a mixture. So that is triple point. So at that particular temperature, the corresponding pressure is 32 millimeters of mercury. Determine the temperature in degrees centigrade when the pressure is 76 millimeters of mercury above atmospheric pressure. And the barometer reads 752 millimeters of mercury. Okay. So when you say the barometer reads 752 millimeter of mercury, what is a barometer used for? It is used for measuring atmospheric pressure. Okay, so the atmospheric pressure is 72 millimeter of mercury. Okay, and what they have given as 32 millimeter of mercury and 76 millimeter of mercury are gauge pressures. And if you look at the first statement, it is very clear. The pressure is 32 millimeter of mercury above atmospheric pressure. So when you start solving the problem, we always solve the problem with absolute pressures. Okay, so first the initial state, you have to convert it to absolute pressure. The final state also you should convert it to absolute pressure. And what they have given is the initial temperature is triple point, and they are asking us to find out what is the temperature corresponding to this 76 millimeter of mercury. So that is what we are supposed to find out. Okay, and but I told you, but I didn't stress it. So in a constant gas thermometer, the moment I say constant gas thermometer, the volume is constant, but the temperature varies linearly with pressure. So you should remember that. So T is proportional to P at constant V. Okay. So you can write down the given details. The moment you see barometer, you have to recognize that it is atmospheric pressure. So if it is atmospheric pressure, then you can write it as P atmosphere equal to 752 millimeter of mercury. Okay. And the gauge pressure, I have written it as gauge comma TP. TP stands for triple point. Okay. And that is 32 millimeter of mercury. Then I have said gauge comma 1. That is another state. Okay. So that state I have taken it as 76 millimeter of mercury. So here I have taken the state points as 1 and TP. So the state points are triple point and another state point 1. Okay. And you can see that the triple point is nothing but 273.15 Kelvin. Okay. What is 273.15 Kelvin in degree centigrade? 0 degree centigrade or 0 degree centigrade. So 0 degree centigrade in Kelvin, you add it with plus 273.15, that makes it 273.15 Kelvin. Okay, so triple point is 273.15 Kelvin. Okay, and here the key is this. The key is the temperature is proportional to pressure. Okay, when I say temperature is proportional to pressure, I mean temperature at triple point is proportional to pressure at triple point. So I have already written that, so I need not write it. It is mentioned here. The pressure at triple point is proportional to temperature at triple point. Similarly, what can I say? The pressure at point number 1 is also proportional to the temperature at point number 1. So because these two are proportional, I can write them as PTP by TTP equal to P1 by T1. Okay. And because everywhere it is millimeter of mercury, I need not worry about the units. The only thing you have to worry about is check if common units are used. If the units are common, then you need not change it. Okay. So because everywhere it is millimeter of mercury, I need not change the units. I can simply use the units. And as I already told you, absolute pressure is what we want. So we add it up with atmospheric pressure plus gauge pressure. Here also atmospheric pressure plus gauge pressure. So I have estimated the values of the pressure at the triple point and pressure at state point number 1. Okay. So now we will be able to compute from these two relations. P is proportional to T, PTP is proportional to TTP, and P1 is proportional to T1. I will be able to estimate the value of T1. And that happens to be 288.48 Kelvin. So I'll give you a minute. You can copy it. I hope the screen is visible to you now, right? The
Yes,
slides are
sir.
visible?
Yes, sir. Yes, sir.
Yeah. Please copy it. I'll just give you a minute. So shall we move on?
Sir, 2 minutes.
Okay. Don't write the question. Just write down the answer alone.
Sir, they asked the temperature in degrees Celsius, sir.
Yeah, you can convert it.
Yes.
You can convert it. You can convert it to degree centigrade. So minus 273 will give you in degree centigrade. So minus 273 will make it 273. That would be 15.
15.48.
degrees centigrade. Yeah, yeah, correct. Okay, so let's move on. Let's move on to the next problem. Okay, here another example is given. Okay, I think this is the second problem. I'm not sure in the problem page. But anyhow, we will proceed with this and then go back. So the temperature scale of a certain thermometer is given by the relation T equal to A ln P plus B. Okay, so here it is not simply linear, it is varying by a logarithmic scale. So it is A ln P plus B, where A and B are constants and P is the thermometric property that we know because T is measured in terms of pressure. So that is a thermometric property. At ice point and steam point, if the thermometric property is found to be 1.5 and 7.5, what will be the temperature corresponding to the thermometric property of 3.5 on Celsius scale? Are you able to infer from this question? They have said at ice point, which means at uh, so at ice point. So ice point, we will take it as 0 degree centigrade. So Celsius scale is something easy for us because 0 is always easy to estimate something. So at Ti equal to 0 degree centigrade, what they are saying is the thermometric property is 1.5. What is the thermometric property? P is the thermometric property. So at 0 degree centigrade at ice point, Pi happens to be 1.5. Is that clear? So similarly at steam point. So I'm using I as suffix for ice point and S as suffix for steam point. So TS is 100 degrees centigrade. So when TS is 100 degrees centigrade, what is the corresponding thermometric property? They have given it as 7.5. So PS happens to be 7.5. That is why I have written it as PI and PS. Okay. We usually take Celsius scale because it is easy. And if you guys are curious and if you are interested, try it with the Fahrenheit scale also. You will get the same answer. Okay. Because the reference points are different. So you will have, the only thing is here they have mentioned it very clearly as on Celsius scale. So we have to do it with Celsius scale. Maybe if you are curious enough, you can try it with Fahrenheit scale also. Okay. The only thing is the scale will change, but the values will be almost the same. Okay. Because they have given the relation T equal to A ln P plus B, then I have to use that relation. So I say at ice point, temperature is Ti and the corresponding pressure is Pi. So I write it as Ti equal to A ln Pi plus B. Then I write Ts is equal to A ln Ps plus B. And I substitute the values. Ti I know it as 0. Pi I know it as 1.5. So I have written two equations. I have to solve these two equations. And you know how to solve these two equations. You can take your calculator and you know how to solve two algebraic equations with two unknowns. You would have done that in maths already in your first and second semester. So you should be able to use the calculator to get the values of A and B. So once you get the values of A and B, now they are saying for a corresponding thermometric property of 3.5, for P equal to 3.5, what is T? Now you know the value of A, P is given as 3.5, B also I have found out. So now I can get the corresponding temperature. So the corresponding temperature is 52.64. Clear? Any doubts on this? If you have any doubts, you can just unmute yourself and ask. If it is okay, then you can go ahead and write it. Is it clear for everyone? Be quick. Shall I move on?
One minute, sir.
Okay. See, the problem is, even in a regular class, people usually find it difficult to follow. But now in an online class, everybody is able to understand. That is really amazing. Are you all guys here?
Yes, sir.
Just switch
Yes,
the
sir.
Sir.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Do you guys clearly know why you are saying yes?
Yes, sir.
Yes, sir. Yes,
Just
sir.
because everyone is saying yes, so many are saying yes. Okay. Um, what we will do is we will take a problem in the problem sheet. So what we have done is we have done problems number 1 and 3 in the problem sheet. Okay. So problem 2, 4, and 5. Okay. Problem 2, 4, and 5. I think you can do it as homework. Okay. Follow the same methodology. Only thing is the equations are different. That's all. Okay. Here we have used the word P, pressure, T equal to A ln P plus B. Okay. I'll share that screen also. So in your problem sheet, we have already solved problem number 1 and 3. So if you take problem number 3, see here it is T equal to A ln P plus B. So the relationship is between temperature and pressure. Okay, if you look at problem number 2, instead of capital T, they have given a small t in degree centigrade. And they have given something called resistance. Okay, so the relationship is between resistance and temperature. Okay, this R naught value is also given here. R naught is the resistance at 0 degree centigrade. So you should find by substituting temperature equal to 0. So if you put temperature equal to 0, you will have R naught equal to RT. Okay, so you have to find out the value of R naught and then you have to proceed with the problem. Okay, and if you look at problem number 4, that is also a relationship between the temperature and pressure. The only thing is here it was a linear scale of order 1. Now this is a cubic equation. P plus Q into TB plus R into TB squared. Okay, where P, Q, R are constants and for different temperatures they are asking you to do it. Will you be able to do it or should we do one problem? I hope you should be able to do it.
Yes, sir. Yes, sir. Yes, sir.
Okay, so now, problem number 5 is also similar. The only difference is the relationship is between EMF and temperature. Okay, here the relationship is between temperature and pressure. Here the relationship is between EMF E and the temperature. Okay, and that too the temperature is of the order 2. So you have a square term also. And also be careful with the units. Here the unit is given as millivolts. Okay, so everything is in millivolts. So when you write it, you should write the answer in millivolts. Okay, now let's try and do this problem number 6. Okay, and this problem has turned out in the semester question paper a couple of times. So it is proposed to construct a new scale with a value 5 degree N. So we are familiar with degree C for centigrade, degree F for Fahrenheit, and capital K for Kelvin. Now they are going to design a new scale, degree N. Okay, maybe like Newton, degree N. 5 degree N for ice point and 2 degree N to steam point. Okay. The pressure of an ideal gas at constant volume. The moment you look at this statement, what should you be familiar with? The pressure of an ideal gas at constant volume is considered as thermometric property. The moment you see this, what should you do? One of you can tell me. The moment you see the word, the pressure of an ideal gas at constant volume, what will you do?
We should have
Temperature is proportional to pressure.
Temperature is proportional to pressure linearly. So you should be able to say T equal to A plus PB or AP plus B. Okay, whatever. Okay, it should be of the form Y equal to MX plus C. And they are asking us to set up a linear relationship between pressure and temperature in the degree N on a new scale. and they are asking us to find out what is the Kelvin absolute zero on this scale, which means if the Kelvin scale reads 0 Kelvin, what should this mu scale read? What is the corresponding value of mu scale for 0 Kelvin? Derive an expression between degree n and Kelvin. Okay, so we are supposed to solve this problem. So let's see how to solve this particular problem. So let me open this. Okay, immediately by looking at the problem, you should be able to say that this is of the form T equal to A plus BP or AP plus B, whichever is that. It should be of a linear relationship. And now what they are asking us to do is, see, if you look at the problem statement, they are saying set up a linear ship between pressure and temperature in degree n on a new scale. But we haven't come to the new scale yet. So before coming into the new scale, we should start with a familiar scale. The scale that we are familiar with is the Celsius scale, and it is also easy for us. So let's start with Celsius scale. Okay, so Celsius scale. So let's start with Celsius scale. So
Sir,
yes,
the screen is not visible, sir.
the board is not
Sir,
visible.
the screen is blank, sir, actually.
Just a minute. Is it visible now? Are you guys able to see it?
No, sir.
Not
No,
yet?
sir, blank.
No,
No,
sir.
No, sir.
still blank.
Is the board visible now? It should be.
Yes, sir.
Okay. So we know that the fundamental relationship is T equal to A plus PB or AP plus B. Because I have written it as AP plus B, I will proceed with AP plus B. Okay, you can also write it as A plus PB. It should be of the form Y equal to MX plus C, that's all. Okay. So now what we know is I start with Celsius scale. So for the Celsius scale, the problem is writing something takes a little bit of time. So this is Celsius scale. Okay, so for the Celsius scale, what we know is if I have a corresponding ice point, then for the corresponding ice point, I'll also have a corresponding pressure at the ice point. So I'll call it as API plus B. Okay, and we know that the value is 0. The ice point in the Celsius scale is 0 degree Fahrenheit. So API plus B equal to 0. The value of Pi is 0. So I write it as 0. So TS will give me APS plus B. Is it not? So this will give me APS plus B. But what is the value of TS? That is 100. Okay. Now I have got two equations. One equation is API plus B is equal to 0. So this is equation number 1. And this is equation number 2. And now what I have to do is I have to solve these two equations. Okay, but the value of pi and ps is not given to me, so I have to simply get the values of the constants a and b somehow. Okay, so what I do is I subtract 1 from 2, so it is 2 minus 1. So if it is 2 minus 1, b minus b will get cancelled, so what I'll have is a into ps minus pi is equal to 100. Am I correct? A into ps minus pi is equal to 100. So now the value of a will be 100. You can also write just as I write. Okay, so don't uh, wait till I finish, because the space is very less and I can't give you time to write every single time. So as I write, you can also write, because it is taking a longer time for me to write. So I get the value of constant a as 100 by ps minus pi. Okay, from equation 1 I can say b is equal to, from equation 1 I can say b is equal to minus a pi, right? I can say b is equal to minus a pi, and the value of a is 100 by ps minus pi, so it is minus 100 pi minus 100 pi divided by ps minus pi. So this is the value of a and b. Is that clear, guys? So I have written two equations, and from those two equations now I am able to get the value of the constants a and b. So once I find the value of the constants a and b, now I can simply write the equation t equal to ap plus b. Okay, a is 100 by ps minus pi, so that makes it 100 p by ps minus pi plus, but there is a minus before this b, so it is simply minus 100 pi divided by ps minus pi. Okay, guys, so now this is for a Celsius scale, so I'll change the color, and finally I'll write this as T in terms of degree centigrade within brackets, that is equal to 100 times P minus Pi. Guys, I don't have space, so please bear with me. The blue color equation is the last equation, by Ps minus Pi, or I can write it as T in degree centigrade divided by 100 equal to P minus Pi divided by Ps minus Pi. and I can call this equation as third equation. Is that clear up to this, guys? So this is for the Celsius scale. Any doubts up to this? Okay, so now
No,
what
sir.
I have done is I have derived a relationship between temperature and pressure for the Celsius scale. But what is the question? They want us to find the relationship between temperature and pressure for the new scale in degree N. Okay, I'll just give you 1 minute. You quickly note down this if you haven't noted it out. If you haven't noted it down, please write it down very quickly. I'll just give you 1 minute because I have to erase this totally if I have to move on to the next thing. Okay, so let me proceed. Bear with me, guys. If you haven't copied, don't worry. It will be there in the recording. You can do it, or I'll also give it in the slide. It is there in the slide, but I just want to make sure you guys follow, so I'm writing it down. Okay, so now what we have to do is we have to do it for the new scale. Okay, so now we have already done it for the Celsius scale. So now let's do it for the new scale. So now we are going to do it for the new scale. And what is the new scale? It is in degree N. That is the new scale. Okay, that is what they want us to find. And I have already used T equal to AP plus B. So what I'll use now is T equal to CP plus D, because I already have values for the constants A and B. So I don't want to confuse it again for the next scale. So I'm simply writing it as T equal to Cp plus D. It is also of the form Y equal to Mx plus C. So no change in the linear relationship, just the constants I have changed so that we do not confuse it with the values. Okay, just like the previous case, we can do it for the ice point. So the ice point, at the ice point, Ti is Cpi plus D. And what is the ice point temperature? That is 5 degree N. Is it not? That is what was given to us in the problem. 5 degree N. And what was the steam point? Ts is equal to Cps in Cps plus D. Is it 15? I remember it as 15. Can anyone?
20, sir.
1 5?
20, sir.
20. It
20,
is 20.
20,
20.
sir.
Okay, okay. It is 20. So Cps plus D equal to 20. Okay. So we have already written up to 3 equations. So let me call it as equation 4. And this is equation 5. So equations 4 and 5. Now what I can do, just like we did before, I can do equation 5 minus equation 4. Okay, that will give me Ps minus Pi into C equal to 15. 20 minus 5 is 15. Okay, so the value of C would be 15 divided by Ps minus pi. So this is the value of C. Okay, just like we did in the previous case, we can find the value of D also. D equal to, from equation number 4, D equal to 5 minus C times pi. So 5 minus 15 pi divided by ps minus pi. Okay, so that is the value of C and D. Now I can substitute it in the initial equation, T equal to Cp plus D. So that gives us 15 times P divided by Ps minus Pi and plus D you have plus 5 minus 15 times Pi divided by Ps minus Pi. You know, writing in board, blackboard is very easy. This whiteboard is horrible. So this is 5 plus 15 times P minus Pi divided by Ps minus Pi. Okay, so now what you should do is, see, if you remember the previous thing that we did, we said T in degree centigrade divided by 100 was P minus Pi by Ps minus Pi. So similarly here also we should write. So this T, you can write it as T in degree N. Okay, so let me change the color. So in this case, how it can be written is T in degree N. Is it not? So this is T in degree N within the brackets. And this 5, which is on the right hand side, can be taken to the left hand side, divided by 15. So this is equal to P minus Pi. Only that which I am writing in blue color, you have to equate, okay? P minus Pi divided by Ps minus Pi. Okay, guys? And this is equation number 6. And you would have written it in your notebook. Now compare equation number 3 and 6. If you compare equation number 3 and 6, okay, and before comparing, equation number 6 is what is giving you the relationship between temperature and pressure. T in degree N is the temperature and P is the pressure. So this gives this equation number 6 gives you the pressure temperature relationship in your new scale. So we have solved subdivision 1. Okay, and then to go beyond, now if you compare equation number 3 and equation number 6, you can find the right hand sides to be equal. The right hand sides in both the cases of equation 3 and equation 6 is P minus Pi divided by Ps minus Pi. Okay, because the right hand sides are equal, now I can say the left hand sides are also equal. So I can say by comparing equations 3 and 6. Okay, I can't write it here, so please do write in your notebook. By comparing equations 3 and 6, by comparing equations 3 and 6, I can write it as T in degree centigrade, T in degree centigrade divided by 100. That degree centigrade, you can put it in brackets. If I put brackets, it is becoming very large. It is difficult for me. Okay, this time around it's okay. So this is equal to T in degree n, T in degree n minus 5 divided by 15. By comparing equations 3 and 6, I am able to get this particular relationship. Is that clear? Okay. So what is the next subdivision? The next subdivision, they are asking us to find what is the corresponding temperature for absolute 0 Kelvin in the new scale. They are asking us to find out what is the corresponding temperature for absolute 0 Kelvin in the new scale. I'll give you one more minute to copy it down. Please copy it down very quickly. Copy it down very quickly. Okay, let's move on. Okay, so now if they are asking us to find, if I read 0 Kelvin in the Kelvin scale, 0 Kelvin in the Kelvin scale, what is the corresponding value in the new scale? That is what they are asking us to find out. And just now we were able to, by comparing equations number 3 and 6, we were able to say T in degree centigrade divided by 100, that is equal to T in degree n, T in degree n minus 5 divided by 15. And we know the conversion between degree centigrade and Kelvin. So if you add something with, if you are able to add T degree centigrade with 273, that becomes temperature of a Kelvin. So if you want temperature in Kelvin, then what you do is you add temperature in degree centigrade with 273. Is it not? Okay. So now if I want to convert degree centigrade to Kelvin, what should I do? I should subtract something in Kelvin with 273. So T in degree centigrade is T in Kelvin. So T in Kelvin minus 273. So now in this equation, I have to replace T in degree centigrade with T in Kelvin. I have to replace this. So T in Kelvin minus 273 divided by 100 equal to this one, T in degree n minus 5 divided by 15. Okay. So now they are asking, or now they are saying, this T in Kelvin is 0 Kelvin. If this value goes to 0, if this value becomes 0, what is the value of this T in degree n? So T in degree n would be First, I have to multiply this entire term. So 15 times minus 273 by 100 plus 5. Check what answer you get. 15 multiplied by minus 273 by 100
Minus 35.
plus 5
Minus 35.9.
minus
35.9, sir.
35.9. Okay,
95, sir.
so your 0 Kelvin 95. So your 0 Kelvin is equal to minus 35.95 degree N. So 0 Kelvin is equivalent to minus 35.95 degree N. That's it. Okay, so that is our second subdivision. What is the third subdivision? Can any one of you read? What is the third subdivision?
Derive an expression between degree n and k.
That's very simple. That's very simple. So what you have to do, you have to replace this T in degree centigrade with T of Kelvin minus 273 by 100, right? So now what you should do, so you can either retain T of Kelvin in one side or T of degree N in one side, okay? So what you should do is, so T in Kelvin is equal to 100 multiplied by the whole thing multiplied by T in degree N minus 5 divided by 15. That's that whole term. This entire term should come here. Okay. And that one, this should be multiplied by 100 plus 273. That will give you the relationship between Kelvin scale and degree N scale. Okay. Is that clear, guys? Were you guys able to follow? I don't know.
Yes, sir.
Yes, sir.
Okay. So now, if you have any doubts, you can ask me. So it's 3:54. We have another 6 minutes. So if you have any doubts or clarifications, you can ask me.
Sir, can you explain the third subdivision once again?
You want me to explain the third subdivision once again? Uh, just a minute, I have to close this open board. Okay, this was the relationship that we saw. Okay, we said T in degree centigrade is equal to T in degree n minus 5 divided by 15. Okay, and I replace this T in degree centigrade with T in Kelvin minus 273. The rest is the same. Okay, and then what I do is I retain T in Kelvin alone on one side, and I'm taking this 100 to the other end. So if I take 100 to the other end, it will be 100 divided by 15 multiplied by T in degree n minus 5. And then this 273 should also be taken to the next end. So that makes it plus 273. So it is T in Kelvin is equal to 100 by 15 whole multiplied by T in degree n minus 5 plus 273. Okay. Is that clear? Is it okay?
Yes, sir.
Okay. Apart from that, any doubts for others? Any doubts, guys? Okay, so with that, one more part of unit number 1 is over. So the basic concepts of thermodynamics, we have done the introductory part, and in this class we have covered temperature scales and pressure. So we have discussed that. So in the next class, we will be talking about work and energy transfer, and we will cover that. And in the consecutive class, we will talk about pure substances, and then we have ideal gas, and then we have equation of states, which includes ideal gas equation of state, Van der Waals equation of state, compressibility chart, and we will do that. Okay. And as I told you, we will be covering that in the next lecture.